Hello student, today in this lecture we are going to perform the stress analysis on this rectangular plate. So let's start with the Ansys Workbench. We'll drag the Ansys structural into a project schematic, and the plate we are going to analyze is basically a rectangular plate having a dimension 60 by 40, and the radius of the hole is 5 millimeter, and the thickness of the plate is 1 millimeter, and 2000 load is being applied on the right side of the plate, and left side of the plate is basically fixed. So we'll solve this problem as a 2D problem, as a plane stress problem. So first we will enter the required geometry material. For this, let's name it new material. For this problem we have Young modulus of 2.1 e power 5 megapascal, and Poisson ratio is 0.3. So after entering the material properties, let's go back to the project schematic and click on right geometry and change the analysis type from 3D to 2D, and again right click on geometry and open our design modeler. Change the unit from meter to millimeter. Select XY plane, click on look at face option and draw a simple rectangular having a dimension of 60 by 40. So 60 millimeter and 40 millimeter. Then apply some constraints as a symmetry to the center line. Now draw a circle here. Give it a dimension of diameter 10 millimeter. After that, simply click on concept and surface from sketch. Click on sketch 1, apply and give a thickness of 1 millimeter and click on generate. So surface will be generated having a thickness of 1 millimeter and 60 by 40 millimeter of dimension. So close the design modeler and open the module. So make sure that the units are in millimeter. Now in this model we have basically three parts. One is the model A4, static structure A5, and the solution. In three parts. In first part we are going to assign the material that we have created to this geometry. Then we are going to perform the mesh, which is basically a division of small elements of the parts. And for the geometry, click on the surface body and assign a material. Instead of structure steel, assign a new material that we have created here. Then in mesh, we have sizing here, we have multiple option here. We'll define curvature. Instead of curvature, we will take as a adaptive. Instead of force, we are going to define the fine option. or you can define the element size to this structure. Let's say we are going to define 1 millimeter as a mesh and click on generate mesh. So there is another technique to refine this mesh, that's called inflation. So inflation is basically a method in which we refine our mesh. So simply in uh, according to our mechanics of material knowledge, we have stress concentration where the notches are present. So here is a hole within the rectangular plate, so there will be a stress concentration, and the chances are high that the stresses are maximum at these notches. So we are going to refine the mesh at a specific geometry at this location. So we will be doing this using a inflation. So this help improve the accuracy of your result in area where the gradients or variations are expected to be high. So we have multiple option in the inflation. So we have number of layers, we have growth rate, which is basically determines how many layers of the elements will be created near the boundary. So you can activate the meshing uh, inflation by clicking on the mesh control of inflation. So for the geometry selection, we are going to select this geometry, click apply, and for the boundary, we are going to select this portion that we have a hole present here. So the number of layers, so for the number of layers, it defines that how many layers of the element will be created near the boundary. So we are going to define, let's say, more than 20 layers. And what is the growth rate is basically the control the element size growth rate from the boundary thickness inward. So next one is basically you can uh, define different option. Let's say we can define first layer by thickness, fine mesh near the this circle, and there is a growth of 1.2 ratio as the layers grow outward. So after that is the static structure option, in which we can define the boundary conditions here, that the what kind of the boundary is fixed and what where the loading is being applied. So we'll apply the fixed port here on the left side of the plate, apply, and we apply a forces on the right side. So please make sure that this edge selection is basically selected here, so we can select the edges of this. So we'll apply the force on the right side and change the force into vector. Instead of vector, we are going to define in the components. So the force are in x direction, so it is 2000 Newton. So after that, we are going to define the what kind of the stresses we have required. So we require normal stresses, and we require the von Mises stresses. We can also find the deformation, so total deformation, and then click on solve. So you can check the maximum normal stress, that is 165.73 megapascals, and equivalent stress is 165.96. As the exact solution of this problem is 166 megapascal, so it is approximate solution, and that is nearly equal to 166.6 megapascal. So as you can see that the trend shows that the maximum stresses are present at these circles, at the notches, so where the stress concentration is very high. Thank you guys.